Alright folks, hello and welcome to this video lesson on section 3.4, solving systems of linear equations in three variables. As usual, I would suggest that you start and stop the video as needed to copy down the important notes into your notebook. So let's take a look at some definitions. First, equations in three variables will look like this: ax plus by plus cz equals d. And notice just how it's a little different. You have three variables here, x, y, and z, instead of just two like x and y, and then a, b, c, and d stand for constants. If they're all zero, it's not a linear equation in three variables, so the book will say don't look at when they're all zero, but that's just the idea there, that you have one of them at least that is a number. A, b, c, and d are constants, at least one of them has to be a number, and then x, y, and z are the variables. So a solution to this equation is not going to be an ordered pair. It's actually going to be what's called an ordered triple, or x, y, and z. Let's underline that. Ordered triples, x, y, z, instead of ordered pairs, because there's three elements to the solution. Now here's an important geometrical point. We do call these linear equations because the variables have a degree of 1. Okay, if you look at the standard form equation I have, it's x to the first, y to the first, z to the first. None of those can be squared, cubed, etc. They can only have a degree of 1. So we call them linear for that reason, because the degree is 1. But if you were to graph these things, they're actually not lines. They actually represent planes. One way to illustrate this is to just take a simple line like y equals x, and say you were to graph that line. If I wanted to put it in standard form, you could do a bunch of transformations. It would become x minus y equals 0. They're the same line. You could do the algebra to convince yourself. But say that's just like a diagonal line that you're used to seeing. Now, that's the line y equals x. If I were to add a new component to this equation, like an x minus y plus z, another variable, instead of just a constant or something, which would keep it a line, well, this quantity is going to change. That z quantity is going to vary since it's a variable. And what's that going to do is that's actually going to move the line. So it's going to take a line, picture this line here, but now this line can move along in a different direction, z units. Either way, it's going to be shifting. And now if you can kind of picture that, well, the line can move here, it can move here, depending what our value of z is. And since it can move a certain way along the quote-unquote z-axis, which we're not going to worry about graphing, but you will see eventually, and it will these kind of lines form a plane. So that's why this line, so to speak, or linear equation, if you add that third component to it, you take an x and a y and you add a third component like a z, a third variable, you actually get a plane that's established. And that works no matter what three variable equation you're working with. If you're working in three variables, an equation in that form is going to give you a plane. Now, I'm not concerned with you graphing these at all. So don't dwell on that. I just wanted to expose you to it and to the fact of the important thing to remember is that these are linear functions even though they don't form lines because their degree is 1. That's what you need to remember. You do not need to graph these. Let's go to the examples. Now, systems of linear equations in three variables can have 0, 1, or infinitely many solutions. So three planes, when they intersect, can intersect at no points, no solution. They can intersect at 1 point and have one solution, or they can intersect to form a line, and that would give you infinitely many solutions. I suggest you look on page 178 because they have some great pictures to illustrate this. When it comes to solving the systems, which are three equations, you're going to use substitution or linear combination. The process is generally the same, but it will require some more work because of there are more equations and more variables. And just a quick note, why not graphing? Well, it's just difficult to graph planes. You'd have to do drawings in 3 dimensions, and it could be done. You can have x and y, and it'll get very complex. You'll have a z-axis, and you'll have a plane intersecting another plane, and I'm just making a mess there. But the point is, it's hard to draw, it's hard to understand what the drawing means, and it's just not cost-effective or efficient for us to solve those by graphing. If you had a computer program, that's a different story. Let's go on to the example. Alright, so let's take a look at this example 1. We're solving the system. We're going to use linear combination methods, and you're going to notice you need a lot of room to show your work with these equations. You're going to be doing multiple systems, doing multiple transformations, and it's going to take a good amount of space to figure out the answer. So keep track of your work carefully. I labeled the equations 1, 2, and 3 as I can refer to them. And the first thing I'm going to do is multiply equation 2 by negative 2. and I'll keep equation 1 the same. So I'll do times negative 2, and equation 1 will be times 1 to get some new equations where one of the variables will drop out. Hopefully you can see which one that is. Alright, so now we're all ready to add these two equations together. And if you notice, the x variables have opposite coefficients, so they're going to add to 0. We wanted that to happen. We want to get rid of one of the variables. And I'm just going to remind you here, be extra careful that you're multiplying each part of the equation by whatever number you choose. One incorrect sign or one incorrect number will mess up your entire problem. So 2y plus 6y will be 8y here. And then we have minus 7z equal to 29. So that's one equation with y and z. We want to get another equation with y and z only. So I want the x's to cancel out again. So let me take equation 2, and this time I'm going to multiply it by negative 3. And equation 3, I'm going to keep the same. And as far as like how do you know which one to multiply by what? Well, you have options. There's different ways to cancel out the y variable, and there's different ways to cancel out the z variable. The bottom line is you need two equations with two variables that are the same so you can solve with methods used in the previous lesson. Okay, so now we're ready to add these two equations together carefully. And again, the x coefficients will add to 0. We'll be left with 8y minus 11z equals 41. And hopefully you can see we're in good position now to use this equation in this system up here, and I'm just going to multiply it by negative 1. If I multiply this equation by negative 1, I get negative 8y plus 11z equals negative 41, which will allow us to add those two equations and and eliminate the y variable. 8y minus 8y adds to 0, and then we have 4z equal to negative 12, divide by 4, and we have found our first official variable, z equals negative 3. So that was a lot of work, but it's only one part of our ordered triple. The rest is going to involve picking two equations, just say the bottom two, substitute our z variable, and then solve that system based on what you're given. So let's plug in negative 3 for z, and that's going to give us 2x minus 3y. I'm going to do a little bit of mental math here to save some space, so just try to stick with me. 5z is negative 15 when I plug in negative 3 for z, and then I'm going to add that 15 to the other side, which will give us a plus 1 on that side, so this will just equal to positive 1. Okay, and you can replay back the tape if you missed what I did there. But now I'm going to do the same type of thing in the second equation, or actually equation number 3. If I plug in the negative 3 for z there, it gives me a negative 12. I'll add it to the other side. That will become positive 11 on the other side of that equation. So I'm going to have 6x minus y equals 11. And let's solve this equation. Or sorry, let's solve this system. You can put a curly bracket around it if you want. That is fine. This one will be, we'll keep it the same. 2x minus 3y equals 1. And this one, let's say, how about negative 3 times negative 3? That will give us negative 6x plus 3y equals negative 33. Oops, I made a boo-boo. Sorry, it's not negative 6x. When I do 6 times negative 3, that is negative 18x. Okay, add these equations, boom. That will give us a consolation there. We have a negative 16x, and we have equals negative 32. Divide by 2 on both sides, and you get x equals 2. And we are almost done. We have two parts of our ordered triple. We need to get that y. What is that y? You are wondering. You want to figure it out. Well, let's plug back in. We need one equation now. Pick any equation you like. I'm trying desperately to find some space over here in the corner with my eraser. Sorry for the mess. I think I have enough room. I'll just take the first equation. And 4x is going to be 8. 4 times 2 is 8. Plus 2y. We don't know the y. And then 3z is going to be minus 9 equal to 1. That's going to be 2y equal to 2. And you can do that math a little more carefully, which will lead to the final answer, y equal to 1. And so in the midst of all these steps and the mess of a problem, we finally have our answer. If I have room for it, we have that, that, and that. And we'll write it up here as a nice, neat, ordered triple x, which is 2, comma y, which is 1, comma z, which is negative 3, and that is how you solve a linear system in 3 variables. Okay, it's time for example 2. I know what you're thinking, Mr. DeRosa, are you insane? How do you think I'm possibly going to sit through another one of these examples? Well, I promise you this one will be a little quicker, but I do want to indicate how you could use substitution if you wanted to solve some of these. You just have to isolate a variable first. So if I wanted to isolate z here, I could move the x and y over, and I get z equals 4 minus x minus y, and then that's like another equation for z. And then let's say I rewrote equation 2 using my substitution. I just labeled the equations real quick, and that would be x plus y plus 4 minus x minus y equals 4. Okay, but remember, don't be too careless. When you substitute into an equation, you should put parentheses around the item you are substituting in for. So if I'm substituting in for z here, I should put parentheses around this entire expression. Oh, and I also noticed that should be a subtraction sign. Sorry about that. Minus, and there it is. And then if you simplify this, you'll get 2x plus 2y, and then we have minus 4, which I'll add to the other side, which equals 8. Okay, remember this. Remember to distribute that negative when you do that simplification. So that's one equation. And now let's say I plugged in the z also into that third equation. We'd get something like 3x plus 3y plus, and then in parentheses we'll have a 4 minus x minus y. So we can get this down to a system of two equations. I want to get rid of these, this equals 12. I want to get rid of another variable in another equation, draw a bar there. Simplifying this, we get 2x plus 2y, and then we have plus 4, I'll add it to the other side, or subtract it to the other side, which equals 8. And now we can solve this system of two new equations, and hopefully these are looking a little interesting to you. If I multiply that second one by -1, we get negative 2x plus negative 2y equals negative 8, and then adding these together we arrive at the result of 0 equals 0. And remember from your or your two systems of two equation days that when the variables drop out, you either get a true or false result. And a true result, that's a check because it's true, will mean that the system has infinitely many solutions. So this system has infinitely many solutions, the one with two equations. Well, as a matter of fact, if you did all legal steps in manipulating the three equation system, and it produces a system of two equations that have infinitely many solutions, well, that is enough to conclude that the original system also has infinitely many solutions. So let me just say that one more time because it's very important. If you do legal solving steps, either substitution or elimination, working with all three variables, and when you eliminate and you substitute, you arrive at a system with two equations that ends up having infinitely many solutions, well, what that's showing is that the original system, or the equations from this original system, are equivalent to the equations from the new system. And so since they were equivalent, the solution set is also going to be equivalent. So if you produce a system with infinitely many solutions, then your original system also has infinitely many solutions. And that concludes example 2. So in summary, this was a long video, a long lesson. These examples take practice. They take a long time. They take fine attention to detail, but you can do it in the same methods that we've been using. So in the summary, we looked at linear equations in three variables, and we said they're planes, but we call them linear because the degree is equal to 1. Next, we saw how you can solve them by elimination or linear combination. And third, we just saw what it would look like if it had infinitely many solutions. And I'll even put no solution in there as well. If you were to produce a system of two equations with no solution, then that would imply that the original system also had no solution. What it looks like as far as the three planes being drawn, you are not required to know that, but it's just for your own knowledge to know that they are indeed planes, and that should follow from what you learned in geometry. Thank you for watching this video lesson, and we will practice more in class.